Bam! Mr. Tarrou. In this math lesson, we're going to take a in-depth look at the dot product, scalar product, or the inner product of two vectors. All three names, depending on what textbook you're using, you'll see that being used not interchangeably within a textbook, but they are the same thing. Scalar product, dot product, or inner product between two vectors. My intention of this video today is not to do any sort of examples you might see in your textbook, but let you and hopefully build some understanding of what it is this formula is describing, or what does it mean geometrically. I'm not going to do a proof per se like this guy was really good at, because I'm terrible at proofs, but I'm going to show you the relationship between these two formulas and the dot product, and then ultimately in the second part of this lesson, what is this product really representing, besides helping us to ultimately find the angle between two vectors. So we have here, given two non-zero vectors, vector u and vector v, we have the dot product or scalar product of vector u and v is equal to the magnitude of vector u times the magnitude of vector v times the cosine of theta. That's a geometric definition and an algebraic definition of your scalar product. If you have each of these vectors in component form, is to do u sub 1 times v sub 1, that's the horizontal components of each of those vectors, plus u sub 2, v sub 2, the vertical components of each of those vectors, or the components in the direction of the x-axis, the y-axis. And now if you have a three-dimensional vector, then you're just going to extend this to plus v sub 3 times u sub 3, which, I said that backwards, but which is the components along the z-axis. And where theta is going to be the angle between vector u and vector v. So we have a diagram here. Both of these are position vectors, if you will, because our initial point is on the origin, but we have vector v, we have vector u, and we have theta in between. Let's look at what's going on with this diagram and show you where these formulas come from and how they're related to each other. So I want us to talk about the fact that we have a coordinate or a point here on the origin, a terminal point at the end of vector v, and another terminal point at the end of vector u. And since the origin is the initial point of each of these vectors, this is going to be the coordinate of v sub 1, v sub 2, and this will be not v, but u sub 1, u sub 2. Okay, and we're just going to simply connect the terminal points of each of these vectors. And you see we have a triangle here. Now, we're just getting into vectors in this scalar product or dot product. An angle theta is between these two vectors, but if we look at these three coordinates, we have a triangle, and we have found angles for non-right triangles before using law of sine and law of cosine. Now, since we have here the fact that we're talking about magnitudes of two sides, and we're going to go into the idea of working with the magnitude of this third side, and we don't know any of these angles, not knowing any of these three angles of the triangle is going to eliminate the possibility of us working with law of sine. So we're going to work this out with the law of cosine. Now that law of cosine that you learned possibly earlier in this year, I'm not sure what course you're taking right now, but in pre-calculus, or maybe even algebra 2, you would have learned that a squared is equal to b squared plus c squared minus 2bc times the cosine, and you always work with some length of a side and the measure of that angle opposite it. So this is going to be equal to times the cosine of angle A. Now, if we have this diagram set up, and this is vector v, well, vector v has some magnitude. It would be the magnitude of vector v. We have vector u, which will have some magnitude. Those are the lengths along those triangles, which we would have applied here and will apply with this law of cosine. Then you have this third vector, which, let's bring in a different variable here. Let's call this, let's call this vector x. Okay, well that's all great, but I want all this work to be in terms of vector v and vector u, not a third variable of vector x. There's just two vectors in this notation. So let's see here. Vector u is the resultant vector of thinking about that triangular method of adding vectors. Vector v plus vector x is going to be equal to vector u. Well, okay, vector u is equal to vector v plus vector x. Now I want to write this in terms of vector v and vector u, so I'm just going to simply subtract both sides by this notation of vector v, and vector u minus vector v is equal to vector x. Okay, we're getting somewhere. With all of this notation now, and the fact that theta, the measure of this angle theta, is opposite this side here, which is now labeled as vector u minus vector v, we have, okay, now also these are lengths, right? The lengths of sides. Well, the length of these vectors are its magnitude. So we have the length of a squared, and we're going to basically be looking at this as our side A, is equal to the magnitude of vector u minus vector v squared is equal to b squared. Okay, that's just the other two sides squared, the magnitude or the length of those two sides. We're going to look at the magnitude of v squared, the magnitude of u squared minus 2 times vector v, vector u, cosine, and then if this is side A, this is sort of like your angle A, and this can be cosine of theta. Now, this is going to take some expanding out here. We have to I'm trying to show you the relationship between these two formulas and how you get the dot product out of it. So how are we going to work out, let's say, the magnitude, this notation here, which is the magnitude of vector v squared? If we look at this vector v right here, kind of try and make it sort of in the same direction and same length. So here's vector v. Well, that vector v is, or has, a horizontal and a vertical component. And if the terminal point here is v sub 1, v sub 2, then this is length v sub 1, and this vertical component, of course, is the v sub 2. And if we want to work out the magnitude or the length of the hypotenuse of this right triangle, we know that just from Pythagorean theorem. It's v sub 1 squared plus v sub 2 squared is equal to the length of this side squared. So actually what I want to do here is say this. Let's fall back to the definition of magnitude. The definition of a magnitude of a function is the square root of the horizontal component squared plus the vertical component squared. Well, that's just, of course, the Pythagorean theorem, except we've taken the square root of both sides. So if I now square both sides of this equation, we get that v sub 1 squared plus v sub 2 squared is equal to the magnitude of vector v squared. So without having to rely on, yet I'm going to use this as we go through this relationship of these formulas, but I haven't relied on the algebraic definition of a vector yet. You can certainly do that again, this sort of like derivation here, or show how we're going to take out this notation of magnitude of vector v squared. That's going to come out and it's going to get replaced with v sub 1 squared plus v sub 2 squared. Now with that little understanding out of the way, we can do this. We can start expanding out this formula, and we get the magnitude of vector v squared is going to be v sub 1 squared plus v sub 2 squared. Same with now, of course, obviously, vector u sub 1 squared plus u sub 2 squared plus, minus 2 times vector v times vector u times the cosine of theta. Now over here, we have the magnitude of vector u minus v squared. Not quite as simple as this notation, so I'm gonna have to get this out of my way, by the way, here. So I'm gonna definitely run out of room. And magnitude is length. And for this vector here, u minus v, vector u minus vector v, I have a terminal and an initial point. So I'm just going to write out that formula. And we have, the length, of course, is the square root of x sub 2 minus x sub 1 squared. Plus y sub 2 minus y sub 1 squared, or u sub 2 minus v sub 2 squared. Now, I just did this part of it. That magnitude is getting squared. So this is all going to get wrapped up in a set of parentheses and square that out. Yeah, this is going to expand out to be quite a big, a relatively long line of algebra here, but a lot of stuff's going to fall out very, very quickly. Well, first of all, this square and the square root are going to cancel. And expanding this u sub 1 minus u sub 2, u sub 1 minus v sub 1 squared, we're going to get u squared plus 2 v sub squared. Same thing here, we're going to expand out this binomial and get u sub 2 squared minus 2 u sub 2 v sub 2 plus v sub 2 squared. And that's going to be equal to our right-hand side. Now on each side of this equation, look what happens. We have a v sub 1 squared on both sides. That's going to cancel when we subtract, say, that term from the left and right-hand side. Same with the u sub 2 squared, u sub 1 squared, and v sub 2 squared. Now what do we have? Well, we have got okay, cleaning that up, we've got this going on here. Each of these two terms have a factor of -2, so we're just going to pull that out. Now here's where I'm going to say this is definitely not a proof, just building up the relationship, and also, hey, showing you that these new formulas that you're coming from, or being given, are being derived and come from other formulas that we've used in the past. Everything in math that you learn is all connected together, and it's just nice to have the time with the camera, you don't have to worry about a bell schedule at school. I can show you this relationship here. We're going to divide both sides by -2, and I said this is why I'm not exactly calling this a proof. This expression right here, u sub 1 v sub 1 plus u sub 2 v sub 2, even though I'm showing this geometric relationship between y, the dot product between vector u and vector w is equal to the magnitude of vector v times the magnitude of vector w. I don't know why I went from u to v to w all of a sudden, but really doesn't make a difference as long as you're consistent. But I'm trying to show where this formula is coming from. It's coming from the use of the law of cosine and how it is the dot product of two vectors. I'm also bringing in here, to finish this and to make this go a little bit quicker, just use the algebraic definition of a dot product. And when you have your two vectors in component form, the dot product of those two vectors using just the component form and not necessarily a given angle in sort of a geometric representation, this is the definition. So this is the dot product of vector v and vector u. I did all this work and did not include magnitude notation here. I am so sorry about that. And that is not only your geometric sort of definition of a dot product and how it's ultimately going to be used. The dot product will allow you to, sort of application of dot product, allow you to find the angle between two vectors, but it also allows you to see this relationship of how your, in a sense, how your algebraic definition is related to your geometric definition of dot product. Now, this isn't the only thing nice if you'd like a little, hopefully enjoying this more in-depth look of your formulas for dot product, it doesn't maybe necessarily geometrically explain what this notation means or how it uses the idea of a projection of a vector onto another one, the geometric sort of meaning of what's going on here in this expression. So let's do that right now. No. So going back to our geometric definition of what a dot product is, the magnitude of two vectors being multiplied together times the cosine of theta. Your textbook might be using the words like projection of a vector. If you're not sure of that, I have a full lesson of what's going on with the projection of one vector onto another one. This is going to be a very abbreviated version of this. But your book might be giving you a diagram that has two vectors with an angle between them, and there's this dotted perpendicular that, while you have this vector u here, with this perpendicular drop down from the terminal point of vector v, you'll have another segment, and I want to use a color I make sure stands out. And I'll drop this line segment just below so you can see it clearly on the camera. This is not supposed to be an arbitrary second line segment, but just a section set off here, and it's going to be in this direction, and it'll be labeled as the magnitude of vector v times the cosine of theta. Let me explain where that's coming from. It'll say that this is a projection. A projection of vector v onto vector u. Okay, well, let's get some white chalk back out so we can see this clearly. Let's call this A, B, and C. And if I look at setting up the cosine of theta, the cosine of theta, as far as this right triangle is concerned, is adjacent over hypotenuse. Of course, we know that. So it's the length of AC over the length of AB. It's adjacent to the angle over the hypotenuse. Oh, okay. So, well, the length of segment AB is the magnitude of, as I have it labeled, vector v. And then solving this for AC, because it's this length here between this common initial point that these two vectors share and this terminal point of C, AC is equal to the magnitude of vector v times the cosine of theta. These perpendicular components, this orange segment is the part of vector v that is on vector u, at least if you're looking at vector v in terms of its horizontal and vertical components. Now you might be saying, hey, this isn't necessarily horizontal, so maybe I need to change my language, but it's the perpendicular components that make up v, where one of those perpendicular components are going along vector u. So it's the part of vector v that extends along vector u. So this is really what you're looking at when I was going to write the summary here in a second, but as you look at the dot product here, vector v times vector u, now I've described this as vector v cosine of vector u, so I can change this around. When you look at this, you're looking at vector u times, real basically, the part of vector v that goes along in the same direction as vector u. So you're really just looking at two magnitudes that are going in the same direction. The magnitude of vector, in this case, or the way this is written, diagram u, and this magnitude or length, if you will, of the vector sort of in this diagram, sort of like AC, or this length of AC, the magnitude or the part of vector v that's along the same direction as vector u. So I hope that I've given you a little bit more understanding and more meaning to these formulas for dot product, so that when you do your homework, you're not just plugging in numbers and things are coming out that, you know, necessarily may not necessarily make any sense. I'm Mr. True. Bam! Go do your homework.